Okay, folks, we're back with the second problem from Chapter 10 in Week 14. This time we're going to look at, problem 14.20 found on page 403. Now, what we're doing here is a paired difference experiment. And as the book points out, the reason for doing this is to try to eliminate some of the variability that can occur when you take two different samples. In the textbook example, they talk about taking your car to the shop after you wrecked it, and you want to get an estimate, and you're considering two different repair shops. And the question is, which is going to be the most expensive place to take your car? Well, the amount of the cost that you're going to incur depends on two things. One is how badly did you wreck the car, and the second is how high does this particular shop set their price? Is it a cheap shop or is it a more expensive place? So we'd like to know the answer to the second part. Is this a cheap shop or a more expensive shop? Regardless of and we want to control out the amount of damage that's been done. So what we've done here is to take the same 10 items to the repair shop. This isn't a repair shop problem, but whatever it is, we're examining the same 10 items. Does it tell us? Yeah, this is two attitude scores to determine the effectiveness of advertising. So we take 10 people, subjects, and give them an attitude test about something. I don't know what it is. Their attitude towards, I don't know, breakfast cereal or something. And they score on a scale of 0 to 100. And I guess high is good. So before the score, the first person, before the advertising was shown, the first person scored 50, the second person 25, and so on. Now they showed them the ad, and then they examined these same 10 people and asked them their opinion a second time. And you can see in every case but one, person number 7, who didn't get it, scored higher than after having seen the advertising than they did before. So what we're asked to do here is to set up a null and alternative hypothesis to test whether or not the advertising made any difference. So let's state that first of all. I've got them all typed in here so I don't have to go fumbling around with my typing. The null hypothesis is that the difference, which we've defined as mu d, which is nothing but the difference between the pre and post, the post and pre, A2 minus A1, the attitude change, which in this person's case is 3, 2, 8, this person really liked it, and so on down the way. Now, what we're really comparing is not the individual scores, of course, but the average score. So let's just calculate some averages, which I've done already. And we find that the mean for the first pre-exposure was 50.5, and the post-exposure was 54.5. But what we're really interested in is the average of the difference, which is column D. We're also interested in the standard deviation of the differences, which turns out to be 3.018. So we're asking, is this difference less than 0, less than or equal to 0, or can we be confident to some level that it is greater than 0? Now the mean difference comes out at 4, and that sounds pretty good, but we know we can't take that as the answer because we have to factor in the variability of that data. There's some chance that it could be at some level of certainty, it could be, there's a chance that it could have been negative, that the difference could be negative. The true population difference could be negative, even though this particular sample came out with pretty favorable looking results. Okay, what are we going to do? Well, we're going to do a t-test. And if you flip to the textbook on page, there we go. There's the confidence interval. Here we are, bottom of page 399. We figure out how to calculate our test statistic, t, and it also tells us how to go ahead and pick our test or critical value, which we'll do in a minute. So here, let me pull in the formula. And all we're doing, as we've done all along, this is getting boring, I'm sorry, but it's the same. We're taking the mean and the standard deviation. The question is, how far away from the mean is this measured in standard deviations? That is, what is d minus, I lost my d bar there, didn't I? No, d bar, my goodness, my equation is wrong here. Oh dear. Now we'll fix that. If you look at it's d bar, oh, I see what I did. D bar minus D0. Now D0 in the first problem was set to 20. In this problem it's going to be 0, so we're going to just subtract 0, which is of course nothing. So it's really the difference, average, divided by the standard deviation of the difference, which I have here, divided by the square root of n. Well, that's pretty easy to calculate, and I'll do that right now. It's 4.19 in a bit. Okay, so that tells us that that's our test statistic. Now the question is, what is our, how are we going to, we need to compare that against something. And we're, of course, going to calculate, therefore, a critical value. Now, I happen to have the t-table here, as you might have guessed from the previous video. Now, the critical value, this is remember, just a one-sided test. We don't have that not equal to thing like we had in the last example. So alpha is taken straight. We don't have to divide it by 2. And we can find our critical values. If you don't trust my Excel formulas, you can flip to the back of the book, and I think you'll find they're the same. Incidentally, you notice I had to double alpha because the function gives us a one-sided, one-sided, so we have to double it to get the I'm sorry, it gives us a two-sided, so we have to double it to get a one-sided. There we go. Okay, so we've got a test statistic of 4.19. How does that compare at the 0.1 level, alpha 0.1? Much greater, so we can reject H0 and accept HA. Same at 0.05, same at 0.0, but look at 0.001. It's just a it's still right there, isn't it? I don't know. I guess we have to, we're going to have to reject H0. No, I'm sorry, the test statistic, the critical value is now greater than the test statistic. So we have to accept H0 at that 0.01. So even though we get a difference of, an average difference of 4, if we really want to get picky have a 0.1% probability of being wrong, we have to accept that there is a chance, sorry we can't be certain, that the advertising made any difference. Well, that's interesting, but let's do the part C of this problem asks us, estimate the minimum difference between the mean exposure attitude score and the mean exposure attitude score, post-exposure and what's the difference, in other words? Well, what we're really asking for when we say that is a confidence interval, right? We want to know what's the difference, the range of differences between the pre and post. What range can D0 fall across? Well, let's do it at the 0.05 level just to start. I'll bring that in. And let's calculate T alpha over 2. The confidence interval, which on the top of page 399 we see as the D bar value, plus or minus T alpha over 2 times the standard deviation divided by square root of n. Same formula we've been using all along. Well, first of all, T alpha over 2 at the 0.05 level is 2.26. And now this is with 9, which is 10 minus 1 degrees of freedom. So that's our that's what we're going to use. And what do we get when we apply that T alpha over 2 value? Well, we get a range that goes from 1.8 to 6.2. So if the boss is only interested in being 0.05% confident, 5% chance of making a type 1 error, we can say, yeah, boss, it's somewhere between 1.8 and 1 and 6.2. And we can be pretty confident, we can be 5% confident that we're making some difference with this add. Well, again, as we did a moment ago, let's say that is 0.001 that we want to have as a confidence level for our confidence interval. Well, look what happens. There's a possibility, not a big one, it only goes down to 0.56, but the range in the confidence interval now includes a negative number, and a negative number means that the post-exposure attitude was worse than the pre-exposure. So again, it all depends on how confident you want to be. Okay, that's it for this segment. Let's go on to looking at the difference, potential difference between not the mean, but the standard deviation, which we'll do in the third video.